Grade 12s, we're on our third day in our exponential functions unit, and I just wanted to take a moment to summarize. You don't have room on your sheet for this, but to summarize what you should have observed yesterday in your 1.1.1 to 1.1.3 exercise sheets. So we had you graph a number of functions, functions that look like 2 to the x or 4 to the x, and then functions that look like a quarter to the x, or, as you know by your rules of powers, 2 to the minus x would be the same as a half to the x. What we were hoping you would notice is that the y-intercept for all of them was 1. So that's a key piece of information to keep in mind when you're graphing. The x-intercept for all of them did not exist. The x-axis, in fact, was an asymptote. For y equals 2 to the x, y equals 4 to the x, they were both increasing. The graphs where 4 to the x was steeper. The quarter to the x, or 2 to the negative x, were both decreasing. Exponential decay. So they would have, and 2 to the minus x would be less. Trying to make those look, that should have been a little steeper. So these are exponential growth. These would be exponential decay. The domain for all of them would be x is a real number. And the range for all of them would be y has to be greater than 0 and be a real number. To continue with today's lesson, we're going to look at solving with graphs. We're going to start with a real-world problem. When Connor was born, his town of Edenville had a population of 35,000. So our initial value, 35,000. The average yearly growth rate since then has been 1.5%. The population of the town is recorded in the graph below. The next question asks us, explain how the characteristics of the graph indicate exponential growth. The initial value is the y-intercept. It doesn't show the left side of that graph, but there never were negative numbers of people. So there is technically an asymptote. It increases rapidly. As time goes on, we're going to have more and more people. And there is a rate of growth where you're adding a percent to a population that is already growing. That rate of growth will be 1 point, just got to check my percent here, 1.5%. That will be our rate of growth. Using the graph, what was the population of Edenville on Ed's 30th birthday? So looking at the graph and eyeballing as best I can, I would say rather approximately the town was 55,000 on Ed's 30th birthday. Using the graph, what was the population on his 50th birthday? Again, we are using our eyes, a smartboard, and a photocopied graph. Our answer will be suspect at best, but approximately 70,000. It is much easier to read off the graph when you're being asked for the dependent variable based on the independent. How old will Ed be when the population of the town doubles in size from the time he was born? So when he was born, the initial value, 35,000. When is it 70,000? Well, we thought that was when he was about 50. So from a graph, we can work both forwards and backwards. All right, this is true. Don't you tell people the dates. When I was born in Orangeville in 1967, the town's population was approximately 5,000 people. When I left for university 20 years later, I was a slow learner really, the population was approximately 15,500. In 2011, Orangeville was 27,975. Okay, do you think my graph is going to look less steep or steeper than Connor's? Is my initial value different? Let's have a look and compare. When I was born, the initial value was 5,000. So my initial value is quite different. 20 years later, it was 15,500. And then, whoops, in 2011, so let's do the math on that, 44 years later, okay, let's put that on. 44 years is 27,975. 427. Okay. How would the graph of the population growth of Orangeville compare to that of Connor's Edenville? Well, the population growth rate changed over the years, so it isn't a perfect graph. It was doing this, and then it did a sort of a different swoop. So it's not a perfect exponential graph, but if we just kind of average those two, the initial value is quite a bit different. It was 5,000. But my growth rate, the growth rate of Orangeville, rather, my growth rate's been huge. The growth rate of Orangeville is quite a bit steeper or larger. I did calculations on it, and it was 4% originally. Connorstown is only 1.5%, and then it jumped to 6.5% later on, so about an average of 5% over the course of those 44 years. All right, now some math ones. To solve an equation, we find the value of the variable that makes the equation true. So, going back to lines, if we have x plus 7 equals 12, we know that we could subtract 7 from both sides. So if I had a value of 5, that would make that statement true. 5 plus 7 is 12. 4 times what is 12? If x were 3, we would have a true statement. It's the same for solving exponential equations. If 3 to the x equals 81, it's an exponential equation, and if x equals 4, I have a true statement. That's lovely if you have nice numbers like 81. But what if you have 3 to the x equals 25? I want an answer that makes that a true statement, and the answer is not going to be pretty. So let's draw the graph of y equals 3 to the x. All right, all of them have a y-intercept of 1. I know this has a rate of growth of 3. So I'm going to triple all my y values on the way up. And I will third them on the way back down and absolutely run out of space on a smartboard. Here we go. My graph doesn't extend far enough, but I know that 3 squared is 9, and 3 to the power of 3 is 27. So somewhere closer to 3 is my answer. So x must lie between 2 and 3, a little closer to 3. Let's see if it's right in the middle. We're going to do some trial and error. 3 to the 2.5. If we type that into our calculator, I get 15.9. Right, not big enough. Let's jump a few. 3 to the 2.8. 21.7, much better. 3 to the 2.9. 22.2. Something's gone screwy here with my numbers. 3 to the 2.95. See if we can refine this a little bit further. 25.56. Okay, too big. And 3 to the 2.92 is 24.73. Oh, good grief. Okay, 3. This is the last one. 2.93 is 25. So x is approximately 2.93. We could see that on the graph. We can do guess and check. All right. So one strategy for solving an exponential equation is by observation. 3 to the x equals 9. I know that 3 squared equals 9. So x must be equal to 2. 2 to the x equals 16. Well, I happen to know that 2 times itself 4 times will give me 16. So x must be 4. Notice these are all nice when you're doing observation. If 3 to the x equals a third, I want to flip the 3, and that will give me 1/3. So x must be equal to -1. And if 5 to the x equals 1 over 125, I know I want to flip it. And to get 125, that would be 5 cubed. So x must be -3. So if you're sharp and you've got nice numbers, you can solve these by observation. Second, you can get these solutions from a graph. 2 to the x. So I'm going to graph y equals 2 to the x. Always has a y-intercept of 1. To the left, I'm approaching the asymptote. To the right, things double. When is that thing equal to 16? Well, it appears when x is 4. The third method for today is to guess and check. Have a calculator handy. If I know that 2 to the power of 4, 2 times 2 times 2 times 2 is 16, and 2 to the power of 5 is 32, then I know my answer lies somewhere between 4 and 5. I think it lies a little closer to 5 than to 4. So let's try 2 to the 4.6 and see what we get. 24.25. So I need a little bigger. 2 to the 4.8. 4.8 equals 27.85, a little too big. And so on. We would refine our search to get the proper answer. And some for you to try, page 66, 9 to 12, 14, and 15.